Hi, this project focuses on predicting 30-day hospital readmissions for diabetic patients. Before getting into the model, I want to start with why this problem actually matters. Hospitals are financially penalized by the Center for Medicare and Medicaid Service for patients who are readmitted within 30 days under the Hospital Readmissions Reduction Program. But beyond the financial side, readmissions are also dangerous for patients. They often indicate treatment or discharge planning wasn't fully effective. To study this, we used a dataset with over 100,000 diabetic patient encounters collected across 130 US hospitals over a 10-year period. This gives us a strong foundation to analyze patterns in readmissions. Our question is, can we build a model that reliably identifies at-risk patients before discharge so hospitals can intervene early and improve patient outcomes?
Alright, so I'm going to talk about the data we used and how we got it ready for the models. Our dataset comes from the UCI Machine Learning Repository. It's called the Diabetes 130 US Hospitals dataset. Basically, it's 10 years of real patient records from 1999 to 2008 across 130 hospitals. After cleaning, we're working with about 99,000 hospital encounters, all from diabetic patients. Now, the raw data was pretty messy, so we had to clean it up a lot before we could do anything useful. First, some columns were barely there. Weight was missing 90% of the time, so we just dropped those entirely. No trying to save that. Second, we filtered out patients who were discharged to hospice or who passed away. They physically can't be readmitted, so leaving them in would just inflate our accuracy and give us fake results. We also made sure each patient appears only once. We kept their first visit to avoid any leakage between encounters. And then for our target, the original data and three categories: not readmitted, readmitted within 30 days, and readmitted after 30 days. We simplified that to just binary. 1 if they came back within 30 days, 0 if not. And worth noting, only about 11% of patients actually get readmitted, so the data is pretty imbalanced. And slide 5 will show how we actually, person 5 will actually show how we handled that. Okay, so after all the cleaning, we ended up with 46 features. They break into a few groups: demographics, age, and race. We wrote a custom parser to convert the age buckets into actual numbers. Hospital utilization, things like days in hospital, number of medications, and how many times they've been admitted before. These ended up being some of our strongest predictors. And then the big one, diagnosis codes. Each patient had up to 3 ICD-9 codes, so there are literally hundreds of unique ones. So instead of one hot encoding um, all of them, we use target encoding, which basically replaces each code with the average readmission rate for patients with a diagnosis. Same thing for medical specialty. And then we were really careful here. The encoder only gets fit on the training data, so there's no leakage in the test set. So basically, we took messy hospital data, cleaned it down to what actually matters, and built features that give the model real clinical signal.
So, I'll walk you through the key insights from our exploratory data analysis. First, we looked at the age distribution versus readmission. Most patients fall between 60 and 80 years old, which is expected for diabetic populations. However, when we compare readmission rates across age groups, the proportions remain fairly consistent. So, even though older patients dominate the data set, age alone is not a strong factor of readmission. This tells us that demographic features by themselves are not enough and we need deeper clinical signals. So, next we analyze time spent in the hospital. We initially expected that longer stays might indicate higher readmission risk, but the data does not support that. Both readmitted and non readmitted patients have very similar medians around 4 days with nearly identical distributions. Like this shows that length of stay is also not a strong predictor, so simple surface level metrics are not just capturing the underlying risk. So finally, we looked at discharge disposition, which turned out to be much more meaningful. This picture represents where a patient goes after leaving the hospital, like to home, rehab, or any other facility. Here we observed a clear pattern. Patients transferred to secondary care facilities have noticeably have higher readmission rates. This reflects that the patient's condition at discharge and the continuity of care also. So overall, Our EDA shows that simple demographic or surface level features are not just enough, and clinical context, especially care transitions, plays a much bigger role in predicting readmissions as well. And importantly, this insight directly carries into a model where discharge disposition becomes the most important feature.
Now for a model section, we compare two tree-based models to predict whether a diabetic patient would be readmitted within 30 days. The first model was random forest, which we used as a baseline. It uses many decision trees and combines their predictions, which makes it useful for handling non-linear patterns in tabular data. We used 150 trees, a max depth of 15, ordinal encoded features, and a 1:5 class weight. Our stronger model was gradient boosting. This model builds trees sequentially, where each new tree tries to improve on the errors from the previous ones. And we used 800 iterations, a learning rate of 0.03, max depth of 10, and L2 regularization of 0.1. We also used native categorical support for this model. Both models use the same 1:5 class weight because missing a true readmission is more costly than a false alarm in a hospital setting. After training the gradient boosting model, we used permutation based feature importance to understand which variables mattered the most. The top feature was discharge disposition ID, followed by number of prior inpatient visits and admission type ID. This makes sense because where a patient goes after discharge and how often they were previously hospitalized are strong signals of future readmission risk. The importance scores also showed that a few features carried most of the predictive value, while many medication features had much smaller effects. Finally, our encoding pipeline helped prepare the raw data for these models. The dataset had 46 features, including several categorical columns. For high cardinality features like diagnosis codes and medical specialty, we used target encoding. For lower cardinality features like race, gender, medications, and ID columns, we used ordinal encoding. Most importantly, the target encoder was fit only on the training data and then applied to test data, which prevented data leakage. Overall, our model section shows not just which models we used, but also why they fit this clinical prediction task and how we prepared the features safely.
Now that we've built our models, let's talk about how they actually performed. We trained both models on 80% of the data, then evaluated them on the remaining 20% they had never seen before. We measured performance on two metrics, accuracy and ROC-AUC, which stands for Receiver Operating Characteristic Area Under the Curve. Random Forest hit 87.4% accuracy with a ROC-AUC of 0.66. Gradient boosting hit 80.7% accuracy with a ROC of 0.68. At first glance, it looks like random forest is better because it has higher accuracy, but that's actually misleading, and here's why. Only 11.4% of patients in this dataset were actually readmitted within 30 days. That means a completely useless model that predicts no readmission for every single patient without looking at any features at all would score 89% accuracy. So accuracy alone tells us almost nothing here. ROC-AUC, on the other hand, is what matters. It measures whether the model correctly ranks high-risk patients above low-risk ones, which is exactly what a hospital needs to prioritize interventions. A score of 0.5 means the model is guessing randomly. A score of 1 means it perfectly separates every at-risk patient from every safe one. To put that in context, researchers who have published papers on this exact same dataset report a ceiling of around 0.67 to 0.68. Our model lands right at that ceiling, meaning we are not leaving any performance on the table. Looking at the confusion matrix, our model correctly identified 746 patients who would be readmitted. These are patients a hospital could intervene on before discharge. We missed 1,517, which is why we applied a 1 to 5 class weight, telling the model that missing a sick patient is 5 times more costly than a false alarm. The 2,330 false positives are manageable because a brief follow-up call is a small price to pay compared to missed readmission.
Our project focused on predicting 30-day hospital readmissions for diabetic patients, a problem that is both costly and critical for patient outcomes. Our model achieved a ROC-AUC of about 0.68, which is consistent with the state-of-the-art ceiling in clinical research, suggesting that we captured most of the usable signal. We found that the discharge disposition and prior hospitalizations were the strongest predictors, emphasizing the importance of post-care environment and patient history. To balance clinical safety with alarm fatigue, we used a 1 to 5 class weight ratio, helping identify high-risk patients without overwhelming providers. One key strength is that our pipeline is fully reproducible and adaptable to real hospital settings. Limitations. The dataset is outdated, uses older ICD-9 codes instead of ICD-10, and lacks unstructured data like clinical notes and imaging. In the future, we would test on newer datasets, incorporate NLP, and explore cost-sensitive and deep learning approaches. Overall, this project highlights how machine learning can support clinical decision-making in healthcare. Thank you.